I think, most important person all over the world about JavaScript, TypeScript, Node.js, and so on. He founded a company in San San Francisco, but he is Italian, but he fell in love with Canada. So he is really an international speaker. But let me present to you Michele Riva.
Thank you. All right, so we are all here to talk about vector databases. And before I start, I'd like to know if there's anyone here that's a database engineer writing on internals of databases. Thank God there's no one. I was so hoping for this. That's awesome. All right. So as Savino said, I'm Michele, and I founded a company. It's called Orama. And we do, OK, no, maybe I can show you. Why? OK. So it's an open source project, actually, that you can find on GitHub. And it started as a full-text search engine. Then we started adding more capabilities, like vector search, hybrid search. So full-text search and vector search combined together. Facets, multi-language, and so on. And nowadays, it's also a complete RAG pipeline you can use in your browser. It's completely free. It's open source. I'm not here to sell it. But I'm here to talk about the journey that I started a couple of years ago when I started this library originally that brought me into falling in love with vector databases. So during my recent times, I've been writing 3 different vector databases, actually. Orama open source, Orama Cloud, and Orama Disco, which is an internal project. It's not open source yet. Though I have to say Orama Cloud was mainly a POC, and the rest of the real-world implementation that went to production was made by my colleague Tommaso. There's also another project, which I'm going to call the Orama Super Secret Project, and we're going to talk about that. And we're also going to talk about why there's a term to be defined under the name. So I want to give a huge disclaimer, because I understand that I've been participating to conferences for, I don't know, 8 years now, as an attendee and as a speaker, and I want to make this very clear. I am not an expert. I have no formal background in computer science, and what I'm expressing here today, it's purely a result of my hands-on experience in writing software. And some things I say might be formally incorrect, but they work, so who cares, right? If you're interested in the topic we're going to discuss today, I encourage you to do your own research, disprove me, and publish your results in an open source fashion. Long live to open source. Let's grow together. So, as I was saying, I absolutely love vector databases. And the first implementation of a vector database I have ever created was pushed to Orama, I think in 2023, yes. And it was a simple PR, add vector search capabilities to Orama. And back then, I only knew a couple of small things about vector databases, of course. I had used them, but the internals, this is what matters. And I didn't really know a lot about it. And if you go see how it performed vector search, so it's basically a brute force algorithm. So I took all the vectors, and I just find similarity matches between all of them. And we're going to discuss how that works later. It's important to notice, though, that Orama was purely meant for browser usage, so I didn't expect anyone to scale a lot. We have Orama Cloud for that, of course. But if you want to use Orama on the browser, I don't expect you to have billions of vectors, so that's still efficient in my mind. So I want to start that journey called the days before writing a vector database you should. So the days before writing a vector database, you should understand what can you build with an actual vector database. And there are so many things you can build with them. You can build recommendation systems, like when you go shopping on an e-commerce and you click on a product and you see all the recommended ones. Maybe some shoes that plays well with your trousers, or T-shirts that play well with your jacket, whatever. That's a recommendation system. That's what you can achieve with a vector database. You can also perform semantic search, which is probably one of my favorite features. So instead of doing keyword search, like I don't know, leather shoes, I can search, I need some shoes for, I don't know, a wedding, and therefore, you give more meaning to your query, and you get more probable results for your purpose. You can do similarity search, image and video search, because image and videos, you have many media that you can convert to vector format. fraud detection, anomaly detection, drug discovery and genomics, voice and speech recognition, and real-time personalization. Spotify, for example, it's a great player in the vector database space, and when you see, I don't know, when you're listening to your favorite song, the next song that it's gonna play, it's a song that's similar to others that you have discovered previously, so there's a high chance that you may like it. And that's all achieved with vector databases. So, if we go back to search for a moment and we compare full-text search and vector search, full-text search is specifically good when you have to perform exact match or keyword search. It's not good when you have context-based match and meaning-based match. We're going to see in a moment what I mean by that. And vector search is slightly worse at exact match, but it's very powerful when it comes to context-based match and meaning-based match. So with full-text search, when looking for the word dressing, I can't tell the difference between dressing for a wedding and salad dressing, right? A query for dressing in green can result in green salads as well in green dresses. And of course, that can be fixed with a good implementation of BM25 and direct acyclic graphs for phrase search. It's very complicated, and you don't really get the same results anyway. Vector search understands the role of individual words in their context, and you can deal with synonyms, slangs, and of course, it has difficulties in finding the exact keyword you may look for. So if you want to look at the process of how you actually create vector search experiences, if you think about full-text search, let's say you want to index the query or perform the query, I love my running shoes. You have to go through some processing like tokenization, so you split the text into multiple tokens. Stemming, so you reduce those tokens at their stem form. For example, running derives from run. Shoes, it's plural, it's derived from the singular term shoe. We remove the stop words, so those words that are so commonly used that gather no meaning in the search query itself. With vector search, that's so different. I love my running shoes actually gets converted into what we call a text embedding, which is an array of floating point numbers, typically. And the days before writing a vector database, you should learn about text embeddings. How many of you has used text embeddings so far? Wonderful. And how many of you knows how they get generated? Okay, I was hoping for no one, honestly. I'm still cool with that. Yeah, I hope you're not gonna hate me. All right, what the hell is an embedding, right? So the definition is a vector is a mathematical object that represents a quantity with both magnitude and direction. In the context of data processing, though, a vector is simply a list of arrays of numbers. An embedding is a special type of vector that represents complex, structured data like words, images, or products in a way that capture the semantic meanings. And they are generated by machine learning models. So what happens is we still have our text input, we tokenize it into multiple tokens, transform those tokens into their numerical form, and we're gonna get there in a moment, process them through machine learning model that has contextual understanding of what you're talking about, and eventually you get back your final embedding. So if you have like, I don't like dressing in green for like that, and the green salad dressing is delicious, even though you have two identical words, the final embedding, it's very different because of the context. And how the hell does it do that, right? Well, that's AI, and it's not my main field of specialization, though I'm deeply leaning towards it. Because the days before writing a vector database, you should understand vector similarity search. So let's say we have this text, and we talk about cat. So we have a model that has been trained in the following way. It starts reading, processing one token at a time, and eventually it says, all right, domestic and cat are always close. And the more it goes and parses the text, and the more it processes the text, it understands that domestic and cat actually goes pretty close. So if we had to draw this into a graph, we actually position them very close. We also notice that facial expressions goes pretty close every time. After facial, that's always an expression in our text. So we position them very close, but very far from cat and domestic, because they might be related, but they're also, they don't appear very closely. So you can think of cat, domestic as tokens, but when we think about tokens, we should think of them as numbers. So those numbers in that particular case could be like the coordinates of those data points on the graph. So, on the x-axis, cat is 2, and the y-axis is 10, same for domestic, expression, and facial, etc. And one nice thing that you discover when you have graphs of that kind is that if you take the numerical form, and again, for simplicity's sake, we are now using tokens that we can all understand. Let's pretend they are numbers for now. So if we take the number representing man on the graph, we subtract the number representing king on the graph, and then we add the number representing woman, we get queen. And here you have a sneak peek of generative UI, for example, AI. That doesn't really, that wasn't necessary. I just found this very nice to showcase. So let's go back to search. If we want to perform search similarity, let's say we have this graph. We have man, woman, kid, and we want to search for boy. So boy does not exist inside of our graph right now, right? What we can do is we have a model that is able to position the boy data point inside that graph. And then we can draw 2 lines, one from towards man and one towards boy. And we will have an angle that is 14 degrees. If we perform the cosine of angle, we have 0.9703, and that's a value. If we do the same with boy and kid, that's an angle of 9 degrees. So if we do the cosine of angle in degrees, we get 0.9903. If we do the same with boy and king, you see that's 58 degrees of an angle. We get 0.5299, which means that boy and kid are 99% similar. Boy and man are 97% similar. Boy and king are 52% similar. So when you're searching for a nice t-shirt for a boy, you also get return results for kids, as they are very similar and highly relevant. All right, back to writing databases. These are some of the most common questions my team and I were coming up with, and I will try to explore some of them. There's no way in the remaining 30 minutes I'll be able to explain all of them, so I will be concentrating on the ones that I find most important and that allows you to get started writing your own. Because the days before writing a vector database, you should start writing a prototype to understand what you actually have to work on. And you have to choose a programming language. And honestly, to be completely honest here, in 2024, if I had to choose a language for such a task, it would be Golang, Rust, or C++. I discovered I'm too stupid for Rust. I'm too lazy for C++, so I'll stick to Go. And I get bullied a lot from my colleagues for that, so shame. And let's start with a serious question now. Again, programming language doesn't really matter. It was a joke. Even though don't use Java, that's not a joke. I do store billion of vectors. Because you see, there's a problem that vectors are typically very large arrays of floating point numbers. And those floating point numbers are typically float 32, which means that every single number in that array is a 4-byte element. Which means that if we have Orama GT small, for example, as an embedding model, which is a fork we host for embeddings, it has 384 dimensions, so 384 for numbers. If we have 1 million of those embeddings, we get a gigabyte and 53 of size in embeddings only. The smallest model from OpenAI, it's 1,536 dimensions, and that gets to 6 gigabytes. And the largest model gets to 12 gigabytes. Now, imagine if we have billions. That's just 1 million, and that's a little data set in today's world. So, again, the days before writing a vector database, you should understand product quantization as an example of compression technique for vectors. That's a bit more complicated. I'll do my best to make it clear. But we start from an original vector of, say, 12 dimensions. where the type is float32, and the objective is coming to a 4-dimensional vector with type uint8, which means basically 4 bytes in total, right? We split our vector into m segments, where m equals 4 in that case, so 3, 3, 3, 3. And we want to map each segment to a fixed integer that we call code. And the way we do that, we use a key-mean estimator, which is basically an algorithm, and I can't stress enough how much I'm oversimplifying this, and I'm deeply sorry for the people who actually understand mathematics better than I do. But the idea is that the key-means estimator, as a clustering algorithm, will group a set of data points into k cluster, where k is the number of total clusters to be created, based on their similarity. So we will have clusters of similarity, and we will be mapping the segment of our original vector, let's say, the little purple one here. We will map it to the centroid of that cluster, meaning that the centroid for that cluster in similarity for the first segment in the first cluster will be 4. Then will be 7 for the green cluster, then 1 for the yellow, and eventually 6 for the blue. And what we get with that simple formula is eventually an original vector, which is 48 bytes in size, and an encoded vector that's 4 bytes only. And I actually want to show you how simple is that with Python, for example. I hope you all can see that. That's a very simple script I made, where we generate 100,000 vectors of 1,536 dimensions, and we reduce them all to 16 dimensions. So that's a production-ready dimensionality for data. Let's hope it works. We never know, right? So if we run python3 main.py, so you see we're training the subspace, so that's part of the key-means clustering algorithm. We are now encoding, so we're already translating the large embedding model into the smaller one. That's going to take around 1 minute, so I will have to find something to talk about while I wait on that. My take is Python is good, but I should have used Java. No, I'm kidding. No one should use Java, right? So give it like a few more seconds. All right, here we are. The original embeddings, 100,000, all combined, gave us 585 megabytes of size. The quantized embeddings, 1 megabyte only. I saved all of those embeddings into files, and we have the original embeddings files, which is 1.29 gigabytes for only 100,000 elements. And the quantized embeddings file is 5 megabytes. And we can see, for example, all right, you see that's only, I'm using head, so that's only the first line. That's the first embedding from the original data set. And that is how you get it quantized. So that's strictly equivalent to that in our algorithm here. So I hope you can see why that's pretty important. There is a beautiful article that I recommend you to go look at. It's called Similarity Search Part 2, Product Quantization. That's very nice. I'll give you a couple of seconds to take a picture if you want. And you also have to remember that product quantization is a lossy compression technique. So multiple segments can lead to the same code, and that's bad because it leads to bad results. So the days before writing a vector database, you should acknowledge the limits of product quantization and understand concepts like asymmetric distance computation, reduced dimensionality with principal computation analysis before running product quantization itself. And you also have to understand that you have to continually run and evaluate retrieval process and fine-tune the number of segments and more. All right. So now we can actually store billions of vectors. How do I query them efficiently? So at the beginning of the talk, I was showing this. Like I wrote 3 vector databases, and we saw brute force, LSH, HNSW. What do they mean? Is there any one of you familiar with any of those acronyms except brute force? All right, yeah, a few of you. Awesome, I'll try not to explain that poorly. How do I choose an algorithm? So as I was saying, in Rama open source, for example, you just go and create a vector and say, all right, let's find the similarity between this vector and all the other vectors in my space. That's not good for obvious reasons, right? But how do I choose a data structure or an algorithm like Kagra or LSH, IVF flat, scan, and etc.? How do I choose one? Well, sorry to tell you, you have to try them and see what you prefer. There are some constraints like HNSW. It's very good with data sets between like 20 gigabytes and 2 terabytes. If you want to go over 2 terabytes, maybe IVF flat can be a good option. LSH is not that performant, while Kagra using CUDA, so GPUs, can be very performant on extremely large data sets. So there's some research to do, and when you actually understand which one you want to use, you also have to ask yourself, should I actually use a library like HNSW lib or FICE or NOI or whatever, or should I write my own? Because honestly, I tried both of them, and I came to the conclusion that I don't want to write any of this, no more. So I still need to understand how they work, though, and my personal preference will always be HNSW. It's a beautiful algorithm that I want to show you, and always remember that the days before writing a vector database, you have to study algorithms and data structures a lot. So let's see for a moment what HNW, it's impossible to pronounce, HNSW is all about. So it's a graph-based indexing algorithm that combines two key concepts, skip lists and navigable small words. In fact, the full name is hierarchical navigable small words. So if we have a skip list, so we say we have a linked list that has 8 elements ordered, and we want to find the number 7. We can use linear search, so we can go first block, is that a 7? No, let's go to the next one. Is that a 7? No, let's go to the next one. And you clearly see why that doesn't scale. But with skip lists, you can actually use multiple layers. So you have a layer 2, which composed to a few elements, a second layer, so it's called layer 1 in that case, that has slightly more elements, and then a third layer, layer 0, that has all the elements. So we can actually have a kind of a divided impera approach where we start from layer 2, we are positioned on the first block and say, is that 7? No, let's go to the next block. And the next block is on 4, so we can say, hey, is that 7? No, there's another block ahead that's less than 7. No, so we go on the second level, so layer 1. We fall into the block 4 on layer 1, and we say, all right, what's the next block? 6. 6 is less than 7, actually. So is there another block ahead where it's 7 by any chance? No, so you should fall down. You're now on layer 0, and you can say, right, I'm on the block 6. What's the next block? That's 7. Beautiful. We reached level 7 in 1, 2, 3, 4 iterations instead of 7. So we save some time. And you can see one very large, like a billion of elements of linked list. That can be impressive. Now, if we combine that concept with the concepts of small world networks, this is where things get interesting. So small world network is a graph where each data point is connected to a number m of other data points, in that case by similarity. So what happens is when I start, let's say I put the point A, there are no other points. I put the point B, there's only one point, so it's got to be the most similar, right? When I put the point C, I only have 2 points, and let's say m is equal to 2, so each point has 2 connections. I connect to both of them. And when I insert D, this is where it's actually getting interesting, because D can perform similarity search and say, hey, you know what, I'm going to connect myself to A and C because those are the most similar to me. And the same applies with E. E will connect to B and C because those are the most similar. But this is how a hierarchical navigable small words looks like. Is that scary? It is for me. So it's hierarchical and preserves the concepts of skip lists. So we actually have, in that case, 4 layers, 3, 2, 1, 0. And the idea is by using, by using exponential distribution, I can ensure that randomly I will insert data points randomly on each layer. But again, using exponential distribution, I make sure that most of the data points stands on the bottom layer, so 0. slightly less points on 1, slightly less on 2, and very few points on 1. So I insert randomly, and every time I insert, I connect to the 2 data points that are closest in similarity to me on my layer, and the 2 points that are closest to me in similarity on the layer directly adjacent to me, so the layer below me. So let's say I insert, for example, a data point on layer 2. I will connect to the 2 most similar data points on layer 2 and the 2 most similar data points on layer 1. Why is that interesting? Well, the trick is having a very good entry point on level 0 when I perform search. And that's because I have to go through a process called greedy search. And by saying greedy search, I mean I start from the entry point, and I say, all right, I have a vector. How similar the entry point is to my vector? Well, that's either similar or not. Let's see the 2 that are the most similar to the entry point. So how similar are them? And I choose the most similar one, and then I go down a level, and I choose the most similar there. And then I go down, and eventually I get to the most similar vector in my space. And that's very interesting. So this is efficient because starting from the topmost layer allows search to make long-range jumps and quickly get closer to the query vector thanks to sparse, high-level connections. But as the search moves down, this is where it fine-tunes itself by using dense local connections in lower layers, ensuring accurate and precise results. And of course, you can say greedy search if you say, all right, confront every single vector you can find in your space. That becomes linear, but in that algorithm, you can specify on each layer, you should confront yourself the similarity at most with 10 different vectors or 100 different vectors, and that's called EF vector, and this is what you should fine-tune when you use such an algorithm. So after almost 30 minutes, we decided that we go with Golang, and we skip on Java. And we are going to use hierarchical navigable small words as an algorithm and as a data structure for performing search and insertion. We discovered about product quantization, and we are nearly 10% there. Because the days before writing a vector database, you should understand how to store your data. And this is where it's the most painful to me right now, honestly. Because, I started by saying, all right, I wrote my first vector database using JavaScript, and I love JavaScript. And I can just use, the concept of inverted index and hash maps, all those data structures that allows you to retrieve quickly elements from an object or from a set. And the idea was, all right, I'm going to use Golang, and I'm going to use the map, and I'm going to store everything inside a map. In Python, that translates to dictionaries. I can store everything inside of a dictionary. In Java, I have no idea. I think they have maps too. But anyway, the problem is it's not so easy. You should use memory mapped files. And then you should also understand how to deal with the caching of those files. You should understand that you can't keep everything on disk, otherwise the access is very slow. And you can't keep everything in memory because you only have so much memory. So if you really think about scalability, my personal suggestion is go and use one of those beautiful libraries right there, like RocksDB. If you go and see how many databases are actually using RocksDB, which is a key value storage written in pure C, and you can embed it in every single programming language, actually. There are so many bindings in so many programming languages. You can use it, and you can let RocksDB map your files for you, keep the hot cache for you, and do the hard job for you. It's not about pride. We have to do a task, and this is a good way to perform that task without losing days and days, reinventing the wheel every time. My personal second favorite is probably Badger. It's the same concept. It's kind of similar to RocksDB. It's written in Go. It's embeddable in a Golang application, and it's brought to you by dbgraph, which is highly maintained. There are also Pebble, LevelDB, TI-KV. It's actually pretty different. It's kind of like a Redis built in Rust that you cannot embed, but you can use within your service. I was also thinking to experiment with etcd, but that's a bad idea, I discovered. So, what happened? So I'm not going to proceed with that one. You can always there writing your own storage engine. Probably you want something very performant, so you're going to do that in C++. And honestly, look at that majestic 25 years old C++ developer. I mean, that's pretty appealing, right? I wouldn't go that route, honestly. The last thing I want to discuss with you today is the days before writing a vector database, you also have to understand how to distribute your data. Because we all make mistakes, bad stuff happens, and we can't think of making a scalable system that only runs on a single node. So we may want to have different servers, maybe closer to the users. And maybe we just want that for reliability, so that if a node dies, we can always use another node, etc. And you have to understand what kind of algorithm you want to use for managing, for example, the quorum on consistency and distribution for the data. You have to understand the model if you want eventual consistency, strong consistency, casual consistency. You want to compare Raft with Paxos or Gossip with Cops. I don't know, Gossip is so fun. I really recommend you to look into that. It's probably, can we use the word fun when it comes to distributed algorithms? I don't know, it's fun to me. But my personal favorite, it's always going to be Raft. I find it to be very elegant. It's not maybe the most performant one, but it's fairly simple to implement and really allows you to scale a lot. It's the consensus algorithm behind most of the applications we use today, and it's very effective. There's also a beautiful library written in Golang, but you can find libraries in every language. That one is from HashiCorp, and I tried, I'm using that in production today, and has always been good, and I'm grateful to HashiCorp for developing this, so I don't have to, and I don't have to look like that 25 years old C++ developer anymore. When you work on this stuff, on consistency, etc., you also have to understand the CAP theorem that I'm not going through in detail right now, but you have to know that in a distributed system, you can't get simultaneously guarantee consistency, availability, and partition tolerance. You can only optimize for 2 out of those. So I highly recommend you to look into that, because this is where you actually have to decide what you want to prioritize. Like, you may want to prioritize partition tolerance and consistency over availability. I don't know. Maybe availability and consistency over partition tolerance. That's more typical, probably. Or consistency, or, availability and partition tolerance. It's up to you, really. Honestly, I don't have a favorite yet. It depends. So we are almost there. And the days before writing a vector databases, we found ourselves learning about what you can build with it, and about text embeddings, similarity search. We learned that we have to use a specific language, probably, to build a prototype. And again, I don't really care about what language people is going to use. I just believe, in total honesty, that there are some languages that performs better than others at memory management. So maybe you want to go with one of those. We understood the vector compression algorithms, that we have to study algorithms and data structures a lot, that we understand how to store our data, how to distribute the data, how to write prototypes. And again, we will always be 10% there, which to me is the most beautiful thing about writing software, because it's never more than 10% done, honestly, which, first of all, will never get us out of jobs, which is cool, but also will always keep us engaged and in love with computer science. And that was actually all for me, and you can follow me on socials, and see you around.